All right, so let's get started. We have a nice little group here, but this is gonna be fun. So this talk is PageRank all the things, which obviously, if you didn't guess already, is about Google's PageRank algorithm. So just to understand where you come from, how many of you know what PageRank is? All right, most of you. Who knows how PageRank works internally? Who knows the mathematics behind it? Who would feel comfortable implementing a PageRank-like algorithm in PHP? All right, so lots of stuff to learn for you. Very good, very good. It's something to get started on. So we'll cover those and some applications of PageRank in this talk. But I do want to start with a story. So I play volleyball, which you could guess from my height, be it at a very recreational level. And this is the story of how I got into this topic. It's about 2.5 years ago. This was my volleyball team at the time. And we were quite a new team, started to playing together in the competition. And well, somewhere halfway through the season, our ranking table of our competition looked something like this. Delta 4, that's my team. So we were somewhere in the middle. We didn't really got used to playing with each other yet. So, well, we're doing quite okay. And our next match that was coming up was against Netwerk, which was second at the time. But one of my teammates, we thought, well, this is going to be a tough match, right? The opponent was ranked second, so that should be difficult. One of my teammates, he went to look at the matches that were already played. And what he noticed was that Netwerk, which was second, had only played against most of the teams at the bottom half of the ranking. So they had all the easy teams, and they hadn't played against the top teams yet. Whereas we had played against some of the top teams, maybe even got some points out of that, and hadn't played much of the lower ranked teams yet. So he said, well, maybe they're not that difficult of an opponent. And I thought, well, I'm a mathematician originally. Can I make this explicit? Can we account for the fact that some of those teams have played against stronger opposition than others? So, well, I want to leave that story for now. Just stash it into the back of your brains. We'll get back to this later. So obviously, the answer to this, that's why I'm giving this talk, was Google's PageRank algorithm, which Google uses internally for ranking web search results. To understand that, we need some mathematics. So let's cover the basics of that. And the branch of mathematics that we're dealing with is called linear algebra. So that sounds, well, pretty scary. What is linear algebra? Linear algebra is the study of the discipline of mathematics that studies vectors and matrices. So what are those? This is an example of a vector, and it's actually just like an array of numbers. The only thing we need to be aware of is it's not like an array that we have like a list or a stack that we can just add elements to at the end or take some from the beginning or something. The size of this array matters. So in this example, we have a vector of 4 elements, and we call that a 4 vector or a vector of dimension 4. And the dimension of this vector is very important. In other programming languages, you can compare this to a tuple, for example. That's how you would implement such a thing in Python. It need not be restricted to integers. For example, we could have negative numbers, rational numbers, irrational numbers, all these floating point numbers. We could put them into a vector. We could even put other objects into a vector, but we won't go over that today. So here we have a 2 vector, which has dimension 2. And 2 vectors are pretty simple because we can imagine them naturally as coordinates, right? If we have a plane, we have a triangle here, and the 3 corner points of the triangle, we can represent them as vectors, as coordinates. So the top right point is 1, 1, because it's coordinates 1 and 1, x first, then the y. The others are at 1, 2, x first, then the y coordinate is -2 over there, and the other is -3, -2. So in this way, vectors represent points on a plane. So what can we do with these vectors? Well, there's an operation that's called scalar multiplication, where scalar actually just means just a number. And we can multiply such a vector by the scalar number. So if we have a vector that is -1.5 over 1, and we want to multiply that by 3, Well, the result of that is actually just both of the coordinates multiplied by 3. So we get -4.5 and 3. So if we have this representation of vector as coordinates, what does that actually mean geometrically? Well, it's actually just when we see this vector as an arrow from the origin to that point, we just, if we multiply it by 3, we just extend the length of that arrow by 3. So we just move it twice as much away from the origin. So that's the vectors. We were told that linear algebra also deals with matrices. This is a matrix. It's again like an array, but then an array of arrays of numbers. A two-dimensional array, if you want. But dimensions, well, we speak about them a little differently when we were talking about matrices. In this case, again, the size matters here. So we have a matrix which has 4 rows and 3 columns. So we call this a 4 by 3 matrix, or a matrix with dimensions 4 and 3. And whereas a vector describes a point in space, such a matrix describes a transformation on such points in space. And we call that matrix vector multiplication. And you must not interpret the multiplication too literal here. We mathematicians rewrite it as multiplication, but it doesn't really have to do that much with multiplication of numbers, or how we normally think of multiplication. So how does this matrix vector multiplication work? If we want to multiply our matrix M by our vector V, that's only possible if the number of columns in the matrix corresponds to the number of rows in the vector. And we will soon see why that is necessary. So how can we calculate something like this? Well, this is a kind of graphical way of how I like to think of this. So we have our matrix and our vector. If we want to multiply them, the first thing we do is we take that vector and we tilt it and we put it on top of the matrix. What we then do is we take that vector and we push it down through the matrix, and every number in that matrix it touches, we multiply the two numbers with each other, right? So the red 8 was in the matrix, the blue 8 from the vector comes through it, and we multiply them. And we do so for all the positions. Then we have a matrix with all the multiplied numbers. And what we do now is we scrape all these results from left to right. We go through the matrix and we add all those numbers. And we collect these on the other side. And we get a vector out. And that is the result of our matrix vector multiplication. Simple as that. We take the vector, put it on top, push it through, multiply everything, and then just add all the things to the left. And we have our output. Not too scary. And what we see here, this is also why the number of columns of the matrix needs to match the number of rows in the vector, right? So what we see here is that when we have a 4 by 3 matrix, we can multiply by a 3 vector, and we get a 4 vector out. And that's kind of what the dimensions of the matrix represent. Let's look at matrices in a bit more detail, right? We had something like this. We had a 3D vector, we put it into the matrix, and we got a 4D vector out. And I'm writing this right to left intentionally because, well, we multiplied things on with the matrix vector multiplication, we put the vector on the right, so it feels more natural to think of this as right to left in this case. So this matrix, it takes a point in 3D space, and out comes a point in 4D space. And if we have multiple such matrices, we can join them together, right? If we had something in 3D space and we put it to a 4 by 3 matrix, we would get out something in 4D space. And if we then have a 2 by 4 matrix, well, such a matrix can convert a point in 4-dimensional space to a point in 2-dimensional space. So we can chain these transformations. And what we're essentially doing at that point in time is that we are transforming a 3D coordinate, some point in 3D space, to a 2-dimensional space, only via a 4-dimensional space. And, well, we programmers like to encapsulate things, so can we hide some way the fact that we are doing this through a 4-dimensional space, right? From the outside, it just looks like we have something 3-dimensional, we want something 2-dimensional, can we make that conversion? So could we describe this transformation, this chain transformation, using a 2x3 matrix? Which it should be, right? Because a 2x3 matrix converts something from 3D to 2D. Well, the answer is matrix multiplication. So we can also multiply matrices by each other. If we have two matrices, n and m, and we want to multiply these, again, the number of rows of the rightmost matrix must match the number of columns of the leftmost matrix. What we do is, well, we take the first column of the matrix and we treat it as a vector. So we put it on top, push it through, multiply everything, then just sweep from left to right, add everything, and we get back the first column of our new matrix. We do the same for the second column of the original matrix, which yields the second column of the output matrix. And we do the same for the third column. Again, put it on top, push it through, sweep left to right, and we get the third column of our new matrix. So here again, we have our results. And we see that a 2x4 matrix, if we multiply that by a 4x3 matrix, kind of the inner dimensions, they cancel out. The output is a 2x3 matrix. Indeed, a transformation from 3D space into 2D space. So visually, it looks kind of like this. We had a transformation from 3D to 2D via 4D, and out comes a transformation of 3D to 2D. And we see here, it doesn't matter whether, if we put a vector in it, we first apply m, and then we apply n. The output is the same as if we would multiply n and m first, and then just multiply that with the vector we have. The most fun matrices in this aspect are the square matrices. The matrices which transform, for example, from 2D to 2D, or from 3D to 3D. Because, well, these transform, in the case of a 2x2 matrix, they transform from a 2D space to a 2D space. So the fun part is, if we have some output from such a matrix, we can feed it right back in. So we can apply the matrix over and over and over again to its own output. And we can view these as geometrical operations. If we have a matrix like here, that actually describes a 90-degree counterclockwise rotation in 2D space. Right? So we had the v over there, and we rotate it counterclockwise around the origin to get the mv value there. And we can see this transformation, it changes every point except the origin. Every point on the 2D space would get transformed to another point, except, well, the cross there in the middle. We could also have a matrix like this, which is actually a mirroring in the x-axis. So if we have the point v there on top, it would get mirrored then to the x-axis, to the point where it says mv. And this matrix, if we have a vector u over there on the x-axis, when mirroring that in the x-axis, it would stay in its place. So we can view this as a fixed point of this matrix operation. And these fixed points, they play a crucial role in PageRank. So let's talk about PageRank. So PageRank was invented by Larry Page and Sergey Brin when they started Google as a way of ranking web pages. And they wanted the best web pages to come out on top when searching, and, well, the slightly lower ranked pages below them. So what does it look on the web? We have two web pages, A and B. And on the web we have hyperlinks, so page A links to page B. And what they thought of was, well, if page A links to page B, it must be because page B is good, or at least significant, right? It could also be, let's look at this horrible web page. Well, at least that would give it a reason why people want to find such a web page. So at least it's significant and we should rank it higher if people are talking about it. So a link from A to B says, hey, B needs to have better score. We could also have a situation like here. Both B and D have incoming links from other pages, but D has incoming links from 2 other pages, whereas B only has links from 1 page. Well, in that case, we should rank D higher than B, because D has more incoming links, so more other web pages think this page is significant, whereas for B only one page thinks so. So well, let's rank D higher than B in this case. In more complex situations, we could have something like this. E here has 4 incoming links, but they're all from other web pages that are not that highly ranked, all from other web pages that do not have incoming links, so no really relevance or significance. Whereas F, it has only links incoming from 3 other web pages, but it does have incoming links from the higher ranked web page E. So well, that counts for more than the 4 worthless incoming links to E. And G only has 1 incoming link, but it comes from our high ranked page F. So well, if a really good website thinks that G is good, well then G should probably be good, right? So what to remember is that the page rank of a web page depends on the page rank of all the pages linking to it, which sounds like a good idea, but is kind of a problem, right? Because to calculate the page rank for a web page, we need to know the page rank of the web pages linking to it. So we cannot calculate these page ranks if they link to each other, because, well, to calculate the page rank, you would need the page rank. We have kind of a chicken and egg problem. So how do we solve this, right? Well, the answer is obviously linear algebra. If we have n web pages in our system or in our web, we create a vector, we call it S, for score of each of these pages. So that's an n vector, where the first element corresponds to the score of the first web page, and the nth element corresponds to the score of the nth web page. And we have an n by n matrix M, and they describe the dependencies between these scores, because, well, the scores of one web page depend on the scores of other web pages. Then we could say that since, well, the scores depend on the scores of others, we could say that we want to find a solution for the equation S is ms. So we were looking for a fixed point of the matrix M. How would we create such a matrix M? Well, if we have pages A and D, and A links to D, well, we would start by having this n by n matrix. In this case, we have a very small web. We have 4 pages, so we create a 4 by 4 matrix. We have columns that correspond with A to D. We have rows that correspond with A to D. And if A links to D, we put a 1 in the column for A, because it's an outgoing link of A, and in the row for D, because it's an incoming link for D. And we also, for every web page, we record the number of outbound links, because we need those later. So now our web gets a little bit more complex, and we also add all the other links that are in this system. So we see that B has 3 outbound links to A, C, and D, and we record that also. And now at the end, we scale this matrix by dividing in all the columns for the number of outbound links. So A had 2 outbound links, so all the 1s in the column for A, they become 1/2. So why does this make sense? Well, we had the equation S is M times S, matrix vector multiplication. And if we would multiply this matrix by this vector, well, we would put it on top, and we would perform our matrix vector multiplications as we showed. And look at the bottom left corner now, right? There's a 1/2 there. In essence, that means, well, the higher page A scores, right? Because we're going to multiply that a half with SA. The higher A scores, the more points the score of D gets for being one of the 2 pages that A links to. So this feels natural, right? This adheres to the principles that we showed, that the higher the page that links to you ranks, the higher your score should be. So the question is now, well, we have this equation. Does it have a solution, right? We have S is ms. M, we can construct that. that's our matrix that we just created. Is there a vector that satisfies this equation S is ms? And something to remember is that it doesn't really matter how high these scores are absolutely. It doesn't matter if these scores are 1,000 and 900 or if they are 10 and 9. It matters how they rank when compared to each other, right? We are using these scores to rank pages relatively amongst each other. So it doesn't matter if we would have an outcome that is a scalar multiple of the score. So we can also look at this other equation where we introduce a factor lambda, which is allowed to, well, be a multiplication factor for the score. If we have a score vector that's still the same direction, it doesn't matter because it ranks the pages relatively the same. And this is what mathematicians call an eigenvalue problem. They call lambda an eigenvalue of the matrix and S is an eigenvector of the matrix. And the question is still, does it exist? Well, the answer is yes. For a matrix M like we have, there always exists such an eigenvector with eigenvalue 1 exactly. The fine print that applies here is that there are certain technical conditions, and we will see them later. But if we have a matrix M like we have here and we apply some fixes to that, there will always be a solution for that. So I'm a mathematician originally, and I would be done here because mathematicians have shown that an answer exists. So that's okay. We don't need that answer. We just want to know it exists. But for practical situations, and since we're programmers now, we also want to calculate that solution. How can we do so? This is the way that Google originally thought about PageRank, but it also helps us in finding a solution. Imagine we have someone who starts surfing somewhere random on the internet, and well, they get onto a page, and then they randomly follow an outbound link of that page. And they get to a new page, and they follow a random outbound link of that page, etc. And somewhere in the room we hide a buzzer set to a random number of minutes, and when the buzzer goes, we check on which page they are. And we do so again and again and again, and we can simulate such, well, multiple such sessions using probabilities. And if we think about this, the higher the probability that someone ends up on a given page, the higher its score should be, right? Because a lot of pages link to it, and it's probably the page that someone wanted. If we think about this simulation, well, we could say we have our matrix here, and the 1/2 there in the column for A and the row for B. It actually says when doing such a random browsing process, and if we see the S's as, well, the probabilities of being on a certain page, then the 1/2 is, when we multiply this, it's kind of, when we are on page A, there's a 1.5 chance of going to page D. The other half chance is going to page B, right? So this kind of illustrates how this matrix M supports this theory of simulated surfing. And if we work with the S's as if they were probabilities of being on a certain page, well, we could just apply this matrix M to S over and over again, and apply M to the new S, etc. And this is what mathematicians call the power method, and it's a way of calculating an eigenvector for a matrix. It's just, well, we have some guess for our eigenvector, we multiply it with the matrix, we get a new guess for eigenvector out, and we repeat that and repeat that and repeat that. And of course we need to start somewhere, so well, we have to take an S0, our first initial guess, and well, as long as it's a reasonable initial guess, we should be fine. And the fact is, well, the question actually is, we could do so, but does this process actually converge to the correct eigenvector? And mathematics says yes, this always converges eventually to the actual eigenvector, at least if we have a matrix M like we have constructed. So how do we do this in PHP? Well, I have written a PHP package, it's on Packagist, it's called Power Iteration. and you can use this to do power iteration in PHP. And underneath it uses math-php, which is a library created by Mark Rogojski, and it has all the logic for dealing with matrices and vectors, etc. It's really powerful. How do you use this? Well, actually pretty simple. We create a matrix M, we create an instance of power iteration, we ask for, as the mathematicians call it, the dominant eigenpair of the matrix M, and from that we get the eigenvector. We're not interested in the eigenvalue because we know it should be 1. And this is actually enough to calculate a PageRank in PHP. Okay, we have to construct a matrix like we shown, depends on your use case, but after that it's pretty easy. How does this look under the hood? Well, in essence it's kind of like this. It's the process we already shown, the iterative process of multiplying a matrix by a vector. So we create an initial guess, which is just a score vector of only ones, and we multiply that by the matrix 1,000 times, because, well, 1,000 iterations should probably be enough, and then we return the eigenvector. So do we really need a PHP package for these 5 lines of code? Well, when really implementing this, there are a number of implementation concerns that you need to think about, like a stopping criterion. Here we used 1,000 number of iterations, but you can also stop based on a tolerance, an error margin between the approximated eigenvector and the real eigenvector. You have to take care of scaling of intermediate results, because if your matrix blows up your vector a lot, you get really, really large numbers, and you get floating point overflows and stuff, well, rounding errors. So you need to scale after each iteration. And you have to do something to prevent reducible matrices. And this is one of the technical conditions I talked about. Because if we do this random surfing thing, and we have a web like this, there are 2 problems that you can see here. One problem is that when someone starts surfing here and they get to page B, they cannot go anywhere anymore because B has no outgoing links. And also, this web is split into 2. If you're in the top part, you cannot get to the bottom part. If you're in the bottom part, you can't get to the top part, so our web is disconnected. So that's something they also thought of at Google, and that's why they introduced something called a damping factor. We call it alpha, and Google uses alpha is about 0.85. And what this does is, well, when we are random surfing, and when we move to a new page, we take alpha probability of following one of the links on that page, and 1 minus alpha probability of, well, just randomly teleporting to another page on the web. It's kind of comparable to entering a new URL in your address bar, following one of your bookmarks or something, and that prevents, well, getting stuck into one page or disconnected webs. Our matrix becomes a bit more complex. It looks something like this, with all the red parts are new. It looks difficult, but it's actually just a process we've just told about, right? We can construct such a matrix, execute PageRank on that, and then we're guaranteed to always have a result, which is the PageRank of our web. So I told you I would talk about other applications of PageRank, because it's not at all limited to web search. In fact, if we think about the general principles of PageRank, we can think of situations where it might be applicable. We can use PageRank for all sorts of analysis of networks or directed graphs, as long as there are several properties. If there's an edge of A to B, it should increase the score of B, right? Just like with the web links. And the higher the score of A is, the higher the score of B should become if there's such an edge from A to B. And there are all kinds of situations that follow these principles. For example, if you want to measure influence in social networks. If, for example, on Twitter, a user A follows a user B, well, we could, if we add an edge for that, and, well, just consider it just like we would do with a web link, we would get the most influential users on our social network. Because if someone follows you and they have a lot of followers themselves, that gives you a lot of influence, right? Biologists also use this to analyze food chains. If species A eats species B, and we add a link for that, and we analyze our graph, we would get out the species of animals that are very important in the food chain because they are directly or indirectly eaten by a lot of animals. If such animals would go extinct, it would have massive effect on our ecology, right? So we can use PageRank to analyze this. We can also use it to analyze our code. If function A calls function B and we add an edge for that and analyze that, we would get all the pieces of our code that are called directly or indirectly a lot of times, that are really hotspots in our code. Maybe these hotspots in your code warrant extra code review or other measures to ensure their quality, because they are really the most important parts of our application. We could do the same with classes. Similar fashion, right? We would find the classes that are used most. We could also reverse it and add an edge between classes when there's an inverse dependency on them. And these finds the number of the classes with a high number of recursive dependencies. The things there's a lot of stuff behind, right? These have many dependencies, directly or indirectly, are just hard to test, for example. There's a lot of logic behind them, they're pretty heavy. We can find these outliers using PageRank. Actually, such a thing is implemented in a package called pdepend. It calculates all kinds of metrics on your code, including CodeRank and inverse CodeRank. You can use it to find hotspots in your PHP code. We can also do the same with dependencies between packages, for example on packagist. If we add an edge, if a package A depends on a package B, we would get the packages that are dependent upon, either directly or indirectly, the most. So these are the most important packages in our ecosystem. If we did such an analysis on, for example, the NPM ecosystem, we would find out that left pad is dependent upon by half the internet, and that when it would be deleted, half the internet would break. It would probably come up pretty high in that ecosystem. So to remember, a PageRank algorithm is not very difficult to implement, but the possibilities are countless, and I hope you take that away from this talk. I still had a story for you, so let's get back to that, right? We had our volleyball competition, which was incomplete. Not every team had played against each other, and we wanted to account for teams having played against higher ranking opponents and teams having played against lower ranking opponents. Well, we can do the same here. We can add an edge from A to B if A lost to B. And in a sense, well, the better A is, the more points, the more score that gives B. Here we have to take something into account, because it kind of matters how big that loss or that win was. If A lost to B 0-3, it would be, well, it should give B more score, more strength than when A lost to B 2-3, right? It also matters for your position on the ranking table, depending on how the scoring system for your competition is. So when calculating this for my competition, I made some adjustments to this algorithm, this construction of this matrix. If A lost 2-3 to B, actually I wouldn't add an edge from A to B, but I would add 2 edges from A to itself. It's like A kept 2 points at home to themselves, and B, there were 3 edges from A to B, so B got 3 points for, well, winning 3 sets against A. Well, I executed PageRank on such a matrix, such a network actually, and well, this was the ranking table as we had it before, and next to that is the ranking table calculated using PageRank, and we can see that network, which was the team that we knew had played against a lot of easier opposition, against all the lower ranking teams, they dropped in that table from 2 to 6, and we we ranked above them. So eventually we played them, and we won big time. Eventually we ended up playing a lot better that season. That's probably because, well, we got used to playing with each other, got better and better, Eventually, we ended up champion of our league. You can see our coach being carried on our hands here in the bottom right. So that's also a reminder that even these systems, they're just models and they can't take everything into account, like a new team that just started out playing together and grows throughout the season, right? It's just a more accurate snapshot of a certain situation, which we can use to make some predictions. But well, as all models, it has its limitations. So that was it. We still have room for some questions. Otherwise, you can also find me around here, ask questions on Twitter. If you attended, please leave your feedback and join in. It really helps me to improve this talk. Are there any questions now? Yes?
Would you recommend any books on learning this linear algebra and stuff like that, like at a beginner level? I'm not sure if that's possible.
Okay, so the question is are there any books or resources I would recommend to learn linear algebra at a basic level? I learned most of this from a university textbook, which are pretty accessible if you had some high school level math. There are numbers of them. I have a textbook by David Poole, I guess. I'm not sure what it's called, but there should be numbers of them, and most of them cover kind of the same material, so it shouldn't really matter which one you take. Any other questions? All right, thank you very much. Enjoy your lunch.